Hi. So it's me, blue jacket, green shirt, still going. What we're gonna do today, we're gonna review Half-Life. I'm gonna do some examples, just walk you through some basic stuff, and that's all you really need to know out of this class. You don't need to have the higher level stuff with it. This is just basics, like just Half-Life. What does it mean? What's the concept? How can you apply it to some simple problems? So we're gonna do all right with that. Now, the basic idea of Half-Life. This is kind of applicable to like the problems, but just let's talk about more of like a broad idea of like what does Half-Life mean in general. So let's say we have four atoms. We have four atoms there. All right. Um, and there's some radioactive isotope that's not stable, meaning it's going to decay. It's going to break down into smaller atoms, and these atoms in their current configuration will no longer exist. It's going to decay. Half-life, the actual idea of what a half-life is, it's how long these isotopes will exist until half of them are gone, basically. So it's basically saying how long it will take for half of these isotopes to decay. So in this case, we have four atoms, right? So the half-life of this would be however long it takes two of them to decay. Clearly, I've chosen a very simple, basic idea here, just to like get the point across. This isn't you don't usually have four atoms or something. But we're looking at this, and so the half-life. Let's say our half-life. So let's say our half-life of this isotope right here. Let's say it is it's got a half-life of 5 minutes. That means every 5 minutes, half of our current sample will decay and will be gone. So let's say we go. So this is. We'll say that this is our time 0. All right. So now let's say 5 minutes have passed. So now we go down here. We've got 5 minutes. They've passed. Okay. So what do we have now? What's left? Well, if the half-life is 5 minutes, that means that two of these things, they're going to decay and they're going to break apart into smaller isotopes, smaller atoms, whatever they might be, smaller elements, different things. But they're, for functional purposes of like being this radioactive isotope that's going to decay, it's gone. So we're going to go from 4. After 5 minutes, we're going to go down to 2. We've now had one half-life take place. So that's one half-life. So one half-life has taken place. Half of our stuff is gone. We're left with 2. So let's keep going. Let's say we get to 10 minutes. All right. So that's another half-life. That's 2 half-lives now. With the basic time interval, just the half-life just represents the time interval in which it takes half of these things to decay and break down. So when we say like one half-life has passed, it's just how many minutes basically. So if it's a 5-minute half-life, that means 5 minutes have passed. When we say 2 half-lives have passed, it's just 5 times 2, 10 minutes. How many particles do we have left if 2 half-lives have passed with our 5 minutes? Well, another half-life here. We're going to break one of these. It's going to decay. You're going to have one left. That just shows you the breakdown. Now, again, of course, this is done usually with like way more, far more atoms. But that's just the basic idea of half-life. All right, that's the simple idea. So let's apply that to a problem. So again, all right, we've got our idea here. This is the note sheet that you can get on the website. It's there. It's available. Check it out. So, and obviously follow along. So this says Krypton 85 uses an indicator light appliances. The half-life of Krypton 85 is 11 years. This is a gas. So first, for problems like this, it's really important that you understand what's important and what's not. So first, the fact that this is Krypton 85 actually means absolutely nothing. It doesn't matter for this problem in any way, shape, or form. So don't think that piece of information is useful to you or something you have to deal with. You don't. It doesn't matter at all. All you care about is the fact that this says that the half-life is 11 years. That means every 11 years, half of the krypton atoms will break down. But again, it doesn't matter. It's krypton. Half-life is 11 years. That's what we care about. So, all right, if we've got a 2,000 milligram sample, we're initially starting with 2,000 milligrams. All right. How much is going to be left after 33 years? So, simple way to do this is all you got to do is say, my half-life is 11 years, and I've got 33 years that are going to take place. How many half-lives will that be over the course of 33 years? Well, 33 divided by 11, that gives us 3 half-lives. That means that, as you do this, it means that you're going to have to basically divide this number by 2 3 times, because you have 3 half-lives. So you're going to start. I'm writing this down really fancy and nice. This is if you understand this, you can see how this is just a very, very, very simple basic thing that you can do here. So don't think that there's some grand amount of work that you got to walk through here. I'm just trying to be really nice and organized to show you everything. So let's say we've got our first half-life. So at our initial zero, so we'll say time. So at our initial of 0 years, 0 years right there, that's a Y. It's supposed to be, supposedly. You got 2,000 milligrams. All right, so we're going to do 3 half-lives. So after 11 years, which is 1 half-life, how much of this is left? Should be half of it. So half of 2,000, 1,000. I'm not even going to show you on a calculator. I'm going to guess you can do that one. So that's 1 half-life. So next we've got another half-life, 22 years. What's half of 1,000? 500 milligrams. And then you keep going, 33 years. All right, so then what's half of 500? 250 milligrams. So as far as half-lives go, this is the first one, this is the second one, this is the third one. All right. So you end up with 33 years have passed, you got 250 milligrams left. That's it. That's all at once. So you can do another one. So it says calculate how much of a 10-gram sample of Americanium remains after 4 half-lives. All right, so it says Americanium, or Americium, sometimes it's pronounced like that, is a radioisotope commonly used in smoke detectors and has a half-life of 430 years. So again, this problem, it presents you with a lot of information that really isn't that important. This is a theme you're going to see in a lot of chemistry problems and a lot of problems in every class that you take from here on out, probably, where you don't always need all the information given to you. Like 430 years, that's cool to know that it has a half-life of that, but for our purposes of solving this problem, that doesn't mean anything. All right, do we care what the sample is? No. We care about 2 things. That we've got 10 grams and that it has a half-life, and that we want to go through 4 half-lives. How does that translate? Well, it just means, okay, you're going to divide this number by 2 4 times. So you're going to go 10. That's our initial starting value. So then after the first half-life, what's it going to be? It's going to be 5. All right, so we got 10 grams down to 5 grams. And then we're going to divide by 2 again. That's going to give us 2.5 grams. So this is half-life 0. So it's important to think of this in terms of a progression of time. So I'm actually always going to diagram out. So we got like time 0. And then we've got our first half-life, our second half-life. So transport it back over here. Now our third half-life, what's 2.5 divided by 2? So you're left with 1.25 grams. All right. And then finally, your fourth half-life, and again, just as a reminder, you're just dividing by 2 each time. So it'll be like 1.25 divided by 2. So that ends up being 0.625 grams. So all I did basically, I just did 10 divided by 2. 10 divided by 2, and then I divided the answer again instead of 4 times. All right, you just divide by 2 4 times. You don't believe me, just calculator. 10 divide by 2, divide by 2, divide by 2, divide by 2. That's it. That's all you gotta do. So don't think again that this is super ultra challenge or anything like that. You can do it. So then you look at number 3 here. It says the half-life of polonium is 3 minutes. It says if you start with 20 grams, how long will it be before only 0.625 grams remains? So I think the simplest way to do this is basically just saying, okay, you're starting with 20. You just should divide it by 2 and just keep track until you end up with this amount remaining. I think that's the simplest means to go about doing this. All right, I think it's by far the simplest way to solve it, and that's important. So you're going to start with 20. And actually, you know what? Why don't you guys try that one? Okay, so hopefully you gave that one a shot. Hopefully you paused the video like I just did, and you tried it. So let's just go through here. And so basically, again, we're just going to figure out how many half-lives it's going to take us to get to 0.625. So we start at 20. You're going to go down to 10. All right, that's 1 half-life. Again, we're simply just dividing by 2. So just 20, 20 divided by 2. All right, that's all we did. It's 1. Then 10 divided by 2, 5. That's 2 half-lives. 5 divided by 2, 2.5. That's 3 half-lives. 2.5 divided by 2. It's 1.25. That's 4 half-lives. 1.25 divided by 2. That will give us 0.625, and that will be 5 half-lives. All right. So that tells us that it will take 5 half-lives to get to this amount of, this amount of polonium remaining. It'll take it that many, decay rounds to get to that point. Now, the thing is, though, the question, and this is an important thing to pay attention to in chemistry too, the question does not ask how many half-lives. It asks how long will it be. Now, it tells you that the half-life of polonium-218 is 3 minutes. You know that it's going to take 5 half-lives, so you're just going to do 3 minutes times 5. All right, and that will give you, what will it be? 15 minutes. I almost said 18, then I was like, that's not right. So the correct answer is it would take 15 minutes, not 5 half-lives for it to decay. You just need to know that it takes 5 half-lives to get to that answer. All right. And then lastly, take a look at number 4. I'm going to pause it again, let you try that for a minute. All right, so hopefully you tried this one. So number 4 is a little interesting in the way it's worded. I don't want you to think that's too complicated or anything either. So it says, iodine has a half-life of 8 days. What percent of the original sample would remain at the end of 32 days? Now, the thing that confuses kids here, the iodine part, again, that means nothing. We don't care about that. We just care about half-life of 8 days, and time frame is 32 days. Now, the one thing that you'll notice that is not here is it says how much of the sample would remain, but it doesn't say how much of the sample you start with. But it does say what percent. So when you have a problem like this where you're not given like an actual concrete piece of information, you're using a percentage. So assume that you were dealing with initially 100%, right? So you're dealing with 100%. That's what we're looking here. The percentage is our actual value that we're going to be dividing by. So we're going to divide this by as many half-lives, by 2 for as many half-lives as we need. So in this case, it says 32 days. So to figure out how many half-lives how many half-lives of 8 fit in 32 days, you just do 32 divided by 8, and that's going to give you 4 half-lives. So you're just going to divide 100 by 2 4 times. All right, so it's going to go 50, that's 1, 25, 2, 12.53, and then 12.5 divided by 2 is 6.25. So we would end up with 6.25%. That would be the correct answer. All right. Now on your homework that you're going to be doing, practice sheet you're going to be working on, it's pretty much all the same stuff. There's a graph it wants you to do. That's not a big deal. It's just, look at this and graph it. You're just graphing the decay. The rest of these are very similar to the examples I just showed you. Like number 1 is exactly like we just did with number 4. You're using a percentage, like what percent of the original radiation. So, you're doing like 100% is where you're starting, and then you're going to go from there. And you're going to say like, okay, well, my 8.61 hours, that's how long. My half-life is 2.87, so you're just going to be like, 8.61 divided by 2.87. Oh, look, it's 3 half-lives, and they'll just go from there. So again, this is really simple. Hopefully you honestly you should be able to figure this all out. Don't freak out with the way some of it looks. It is just dividing by 2, basically. Just then you got to figure out how many times you got to divide by 2. So hope that's good. Take care. Do good. Don't fail.